The last talk of the afternoon is titled What We Learned from Epsilon Aurigae About Its Recent Eclipse by Arne Henden. Just a little summarization for you. Every 27.1 years, Epsilon Aurigae is eclipsed by a mysterious dark cloud. The most recent eclipse started in 2009 and ended in late spring of 2010. Thousands of amateur astronomers contributed observations of the eclipse, and professional astronomers worldwide trained their telescopes on the unique event. During this presentation, Arne Henden, the director of the AVSO, will talk about the competing models of the system and what we think happens every 3 decades. Ladies and gentlemen, Arne Henden.
Thank you. I actually get to start 5 minutes early. I like that. So I want to talk about this weird star. And I learned about this back when I was in graduate school. It was undergoing its eclipse in the 1980s. And I thought, gee, that's an interesting star. And then promptly forgot it because I was busy doing other things. And then as I became director of the AVSO, lo and behold, the next eclipse was due. And so we put in for an NSF grant to get some citizen science support for the eclipse. And so a lot of what I'm going to be describing today are the results from that grant, as well as the amateur contributions from elsewhere and some of the professional work. The eclipse is still not quite finished. It takes 3 years to complete, and so we're waiting for Epsilon Aurigae to come back around from behind the sun, which it should be doing any day now. So let me first start out with what I say are the importance of eclipsing binary stars. They're just everywhere. They were some of the first variable stars that were discovered. Examples of those are Beta Lyrae and Algol. The light curve itself, if you just use the light curve, gives the period, the orbital inclination, because you know that it's in the plane of line of sight. The temperature of both of the stars, because you can look at them with colored filters, and gives you the mass ratio and a bunch of other things. You combine that with spectroscopy, which gives you the radial velocity information, and now you have a full description of the entire system. So it's really pretty cool. And for white binaries, those are ones where the separation is such that the two stars don't interact with one another. You actually can look at systems like that and know that the stars in those systems are evolving as if they were by themselves, single stars. So it gives you a handle on how stars evolve if there's no other complications. The close binaries, where you have mass transfer that occurs between the two stars, you no longer have separate evolution. The two stars are evolving together, and you get some really neat effects. All novae are formed from close binaries like that, where mass is accreting onto a white dwarf, and type 1a supernovae also occur from such interactions. And then because we know and understand single stars real well, you can actually use wide binaries as standard candles, and you can actually measure the distance to nearby galaxies by looking at stars. Or you can use the type 1a supernovae and be able to determine distances to galaxies even further out. And the other thing about it is, when you're talking about two stars that are in the same system, they obviously formed together in that system. And so all this stuff funnels into the theory of planet creation, because instead of having two stars, you have, in our solar system, a star and planets instead of a second star. Jupiter's, you can think of as sort of a failed star. So binaries are really interesting things. It works. However, the projector is never up to the standards of looking through the telescope. This is probably one of the most famous binaries. This is Alberio. So you have here a nice blue star and a nice yellow star. If you look at it through a telescope, Separation is about 35 arc seconds, and to me, the yellow star actually looks kind of gold. But the color difference is really striking and apparent, and it would be even more striking if this were a true binary system. The problem is that at the distance of this system, which is about 390 light years, the two stars are so far apart that if they are in gravitational attraction to one another, the period of that orbit would be something in the order of 100,000 years. So most scientists feel that these stars are just sort of in the same area of the sky, but they don't really belong to the same system. However, the star on the right, the yellow star, which is a K star, actually has been found more recently as being a true binary system. It's two stars that are, if you can see them in the sky, they're about half an arc second apart, and the orbit for those stars is about 213 years or something like that. So that's a true binary. So this is sort of a visual binary plus a true binary. But it's really a fun star to look at. I think most telescopes end up looking at that if they want to look at a binary star. But if you look at the distribution of binaries in our own galaxy, here are the ones that we know of today. And so this is a distribution in which the vertical axis is the number of these kinds of binary systems that are known. These are eclipsing binaries, so they're only the ones that are in the line of sight. Versus period. And so this only goes out to 5 days. And you can see that the vast majority of the systems are these things that are under 1 day in rotation of the two stars. So that means that one star is going around the other one in less than 1 day. And so these things are very close to each other. They're moving very rapidly. And the reason that you see so many of them at short periods is because the stars are so close to one another that geometrically one is always going to be obscuring the other, even if they're tilted at high inclinations. And so that's why you see lots and lots of these. And the other reason is this statistical discovery space, in that if it's less than a day, you're more likely to discover it than if it's a long period. All right, but what about the other extreme? Out on the tail, I showed you out through 5 days, and the number count was getting very low. Here are the ones that we know of that are in the multi-year category. So if you look at the bottom, these are stars that have periods of the eclipsing period is like 2.7 years for Zeta Aurigae, which is right next door to Epsilon. And if you go up from there, there's 1, 3.4, 9.3, and up at the top is Epsilon. 27.1 years. That is the longest known eclipsing binary system. And as the periods get, or the orbital periods get longer, then it means the stars are moving slowly too. So that as they go and transit across the disk of the other star, that transit or eclipse takes longer. For Epsilon, it takes 670 days. So it takes almost 2 years to go from one side of the star to the other. So if we look at the star itself, Epsilon Aurigae, it has eclipses, like I said, every 27 years. But we only see one of the two stars in the system. It's an F star. We know it's an F star because you can look at the spectra and it looks like a normal F star. But you don't see the companion. The companion is completely dark. And if you start looking at the eclipses themselves in radial velocities and a few other miscellaneous things, you find out that what you're really seeing is you don't see a star, a dark star passing in front of the other one. What you're seeing is a disk of material, a cloud of material that's passing in front of the F star. And the most recent eclipse started in 2009, which was kind of a fortuitous date, and it's just now ending. The last reports in sort of the May time frame before it went behind the sun showed that it's starting to get close to its normal brightness. But this particular system is really weird. And I'll show it to you in a minute. If you want to find Epsilon Aurigae in the sky, well, there's Orion, so that's an easy one to look at. Taurus is sitting there, and if you go up into Capella, it's just right adjacent to Capella. Really easy star to find. It's the third magnitude star. And as I was showing you this morning, or at noontime anyway, this is the way that a lot of the amateurs are finding and estimating the brightness of the star, is that you take the star itself and you look for stars that are nearby that we know the magnitudes of, and what you try to do is interpolate. You find a star that's brighter than Epsilon, you find a star that's fainter than Epsilon, and you estimate that it's somewhere in between the two brightnesses. And that way you can report the magnitude of the star. This particular picture would look nice in a dark room. It was taken by an amateur friend of mine in California. And what it basically shows, you can actually see it a little bit. You see lots of stars over here, and you don't see any stars over there. There actually is a dark cloud that's right adjacent to Epsilon Aurigae. It's Lens 1457 or something like that. We'll see it in a couple of minutes. But it's, you know, is it really associated with Epsilon? For instance, here's the dark cloud. Is this star physically associated with it? Are they at the same distance? Or is it just a superposition of the two objects? So the history of this star, it was actually discovered in 1821. And I can't imagine people looking at the sky and being able to, for the first time, see something fade as little as this star does. It's only like 3/4 of the magnitude. But he said he saw the star seemingly so dim compared to Zeta and Eta that it would barely be recognized. Has anyone else seen this effect? And then people started to look at it, and it went into eclipse again in 1847 and again in 1874. And by the time 1903 eclipse came around, they actually determined what the period of this particular star was, the 27 years. But it turns out that every eclipse since 1821 has actually been observed, and we actually got data for that star. Now, 27 years is kind of an interesting time frame. First of all, it's about the research lifetime of astronomers. So like I said, the last one came around when I was in graduate school, the next one will come around when I won't be around. And so it's a lot like Halley's Comet is for lifetime of individuals. And that 76 years is a really round number. 27 is a nice number for astronomy. Not only is this sort of the research lifetime of astronomers, but it's also kind of the time when technology improves to a point where you can use new techniques. 1901 was photography. In 1929 eclipse, they were starting to work with lead sulfide photocells. In 1955, they were doing photoelectric photometry. 1983 was the beginnings of CCD photometry. There were a few imaging systems then. And then most recently, we've been doing actual interferometry, measuring the stars themselves, the disk of the star. So here are the last few eclipses before the 2010 one. And so they're all superimposed on one another. They've been shifted with respect to one another just so that you can see the details. You can see that in all of them you have this kind of wiggle that's occurring in the star, and it also occurs down at minimum and everything. The F star itself is a pulsating variable, and so it is doing its little wiggle in addition to the eclipse caused by the disk. And the other point that people were wondering about was right here at the middle of the eclipse, at least in the 1983 eclipse, it seemed like there was a central eclipse brightening. Something was going on in the middle. But because these eclipses last for more than 1 year, it goes behind the sun. So it went behind the sun right there, went behind the sun there, went behind the sun there. And so basically you miss a piece of the eclipse. So it's kind of a difficult one to cover completely. This is the artist's conception for what the eclipse looks like. And if you could see this, I can tell you what it looks like. Basically, you have this dark cloud that's sitting here. The F star is sitting over here, and something in the center of the dark cloud is also there. And you assume there's something there because why would a dark cloud just be sitting in open space? There's got to be something that's sitting there that's gravitationally attracting the dust. And so the concept is this is probably a B star of some sort and an F star over here. One of the things off of the Citizen Sky project that we have not only are we getting people who are going out and measuring the brightnesses of Epsilon Aurigae throughout the eclipse, but we're also getting a lot of contributors in other ways. And in this particular case, Ryan Thiem is a graphics artist, works doing web design. And so he's done a lot of very interesting models and drawings of what the system must look like. So let me tell you about Citizen Sky. This is still ongoing. It was a 3-year project with NSF, and we're just finishing up the 2nd year. September will be the end of our 2nd year. And it coincided with IYA 2009. That's how we were able to promote it as a citizen science project during the year of astronomy. And we concentrate primarily on this eclipse. And so the concept is to take the average citizen all the way through from learning about the system, making observations of the system, doing some analysis, and actually publishing some papers. We have a referee journal on variable stars as part of our organization, and we're going to hold a special issue in which we publish papers from some of the researchers participating in the Citizen Sky project. Now, I said that we're coming out of the eclipse, but it's a 3-year project, and the reason is that we need to have observations out of the eclipse so that you can actually see where the eclipse stopped and so on. And so as the star comes around the sun, you can still make valuable contributions. You shouldn't assume that, okay, the eclipse is done with, the project is over with, I'll go on to something else. Contribute for another year or so. And any kind of technique, whether it's visual or CCD or DSLR or anything, all those are welcome. All right, so what are some of the questions on Epsilon Aurigae? Well, how far away is the system? It's not so easy to find distances once you get out to sort of 500 parsecs or something like that. What is that nature of that unseen companion, the thing that's hidden behind the dust cloud? And what about the dust cloud itself? What's its size? What kind of composition? Is it made out of, carbon grains of what size and so on? What are the masses of the 2 stars? It turns out that all you know is the mass ratio. You really don't know which mass is, if the mass is 3 masses for one and 10 for the other, or 1 mass for one and 5 masses for the other. They all average out. What is the evolutionary history of the system? That feeds into what are the masses of the stars. And then this dark nebula that's next to it. If this is a young system and you have a dark cloud next to it and they're at the same distance, then maybe the star was formed out of the dark cloud. If it's an older system, then there may not be any relation whatsoever. But it's an interesting superposition, and I always wonder about things like that. So there's 2 basic theories for this particular star system. The first is you have an Eps Aur that is the main sequence Eps Aur, basically. So it's a high mass, well, not main sequence, supergiant. Basically a fairly young star with about 15 solar masses. And then if that's true, then whatever is inside of the disk has to be young as well. And so it's a young stellar object. Inside of probably the disk that the star is forming from. So that's the high mass theory. The low mass one is, this is a later stage of stellar evolution. The Eps Aur is no longer, it was probably a typical main sequence star, had high mass, it's now evolved off of the main sequence, it's lost all of its mass to speak of, and what you're left with is a star that's about 4 solar masses. And then what you have as a companion then has to be a main sequence B star, and the disk then is the debris from the evolution of the F star. So the material that's sloughed off of the F star has fallen onto the B star and is now hiding the B star. The trouble is both those theories meet the observational material as before this particular eclipse started. So they couldn't decide which one was the right model. They're quite different. This is a schematic diagram that Jeff Hopkins came up with to show you basically the size of the system. If you look at it in relation to the Sun-Earth system, Here's the distance from the Eps Aur, the disk and everything is something like out of the orbit of Neptune. So they're fairly far apart, and that's why it takes sort of 27 years. It's kind of like Neptune's orbital period. The idea for the high mass system is 15 solar mass star, something like 100 or 150 times the sun's diameter. And then inside of this disk was something that had to have the right masses in order to get the mass ratio right. And the only way they could come up with the right mass ratio was that there were two stars inside of the disk, sort of a binary system of its own. And that, then you have two stars, you have double the mass, and everything fit together. The low mass system then only has to have a single star inside of the disk because now you decrease the mass of the primary. So the distance, the only distance measurements that we really have are from Hipparcos. And this is a satellite system that went up in the 1990s. And it measured the distance to Epsilon Aurigae at 653 parsecs, plus or minus 551. So that basically means you don't know the distance to the star. So if you go by sort of parallactic distances, we're going to have to wait until Gaia goes up before we're going to be able to find the distance to the star. There are some other ways in which you can infer the distance. If it is an F star, then you know how bright it should be, and so then you can decide the distances. But then that's model dependent. That's not an observation. So those are why you get all this arguments in the literature about it. The spectroscopy, there seems to be some helium absorption near the mid-eclipse. And in order to get that, you need to have something in there that has a temperature of about 25,000 degrees. And that, of course, is your D star. And then Spitzer itself was used to measure the system, and it was able to determine that the direct signature of the disk temperature, about 550 degrees Kelvin, and that the grains of the disk are large, they're not really fine grained stuff. So that gives you a little bit of indication about the disk. The full spectra of this thing, Don Gordon came and presented at one of the AAS meetings of the complete spectra of this thing from the ultraviolet to the infrared. And you can fit it with three different components to the system. The one over here on the right is just the temperature of a 550-degree black body, which is presumably the dust surrounding the companion. In the middle here, it correlates very nicely. Here it is, right there. Sort of the dotted line. That's the Eps Aur. So that all fits together. And then in the ultraviolet, this little piece here matches very well with the B star. Okay, so we have the same concept. We actually have seen the B star. However, most people think that what you're actually seeing is the reflection of the spectrum of the B star off of the dust. So we still haven't seen the B star directly. During eclipse, this is a third magnitude star. And one of the neat things that's happened since 27 years ago is that there are a number of amateurs now that are doing spectroscopy. And most of these are in Europe, in the UK, and also in the France and Belgium region. And they're actually doing time series monitoring of Epsilon Aurigae during the eclipse. And these observations come from Robin Leadbeater. And this, for example, he's looking at the potassium line at 76 to 99 angstroms. And as a function of time, and you can see actual structure changes. If you look at what's called the equivalent width, which is basically you take the depth of one of the spectral lines, and you say, okay, what's a rectangle that is equivalent to that particular line? Narrow it in, make it deeper, it goes down to 0. That's what the equivalent width of the line is. If you do that, this is the potassium equivalent width from these spectra. And you can see that as the eclipse started, that it basically goes in stair steps. So what he was considering here is that you're actually seeing structure in the disk of the dust disk around the other star as it starts eclipsing some of the Eps Aur. In photometry, there were a lot of people who were studying the star. We had over 1,000 people in the Citizen Sky Project who contributed data, but there's also a number of amateurs within the AVSO itself, and some of the European amateurs who were doing precision observations using photoelectric photometers and the like. Jeff Hopkins is an amateur in the Phoenix area. He runs the Phoenix Hopkins Observatory, and he has a campaign website dealing with both the 1983 eclipse that he observed and now the 2010 eclipse. He's collected a lot of observations as well. And so we not only had the spectroscopy, but we had UV, R, and I optical photometry, plus there's now infrared photometers that you can buy commercially from Optech. And so there's J&H photometry as well. And like I said before, you saw that little pulsation stuff that was going on. We're actually starting to look at the Eps Aur and trying to understand the Eps Aur and its pulsation period. And that's another reason for observing the data outside of the eclipse, because we want to see the pulsation and try to understand what's going on with it, so you can sort of subtract it out of the eclipse and get a separation of the two. Now, I mentioned before that Spitzer was actually able to detect the dust cloud itself, and if you were at secondary eclipse, so that the Eps Aur then is covering the dust cloud, then with Spitzer you could actually probably see the decline in brightness of the system due to the eclipse of the dust cloud. The trouble is that 27-year period. 27 years ago, there weren't satellites up that were doing infrared observations that would be able to detect this system. And well, in 13 years from now, so it's actually not 13 and a half years. 13 and a half years from now, when the secondary eclipse will take place, who knows what spacecraft is going to be up there and able to look at the system. But if there is one, I'm sure they will. So here is the optical light curve of Epsilon Aurigae, starting from basically the ingress of the eclipse down through this totality area and then up through the egress and where we are today. You can see that here again is the mid-eclipse, not mid-eclipse, this is the solar conjunction, and there are actually people who are able to observe through solar conjunction. The star is at plus 43 declination. And so if you're up in Norway and places like that, it's a circumpolar star. And so they are actually able to do some observations. But it's a circumpolar star in an area that's above the Arctic Circle, which means, that you have a bright sky. And so these observations tend to have lots of scatter. Again, this is blue, green, which is basically visual, red, and far red, the I band. And you can see that the photoelectric and DSLR and CCD observations closely match the black dots, which are visual observations. The visual observations tend to be in these lines because the visual observations are reported with sort of a 10th of a magnitude granularity. You don't get somebody who's reporting to 0.15 of a magnitude. It's either 0.1 or 0.2. And so it shows up as that granularity. The really interesting data that's come out with Epsilon Aurigae has been the interferometry. This has been spearheaded by Bob Stencil at the University of Denver and his graduate student, Brian Kloppenborg. They're using the Tara array at Mount Wilson. I'll show you a picture of that in just a minute. And what's interesting is it's the first time we can actually look and get an image of the star itself, and during the eclipse to boot. And it's really hard to do. This thing, like I said, is 600 parsecs away. It's 2,000 light years away. And so the Eps Aur, even though it's 100 times bigger than the sun, only is 2.3 milliarcseconds in diameter. So there's no way that you can do it with any telescope on Earth except for an interferometer. And the way you do it with an interferometer is that you use a set of telescopes to sort of emulate a really, really, really big telescope. In the case of the Tara array, it's 6 1-meter telescopes, and they're basically, here's the beam combining ability. There's a set that goes out here, a set that goes out there, and a set that comes down here. So there's a dome for one of the 1-meter buildings. And so the maximum baseline on this thing is about 331 meters, which gives it a theoretical resolution of about half a million arc seconds. And so you can actually then start getting images of the star. And so here are some of the images that Brian was able to get with the Char array. So this is in 2008, prior to the eclipse. This is the sort of resolution that you get with the system. So if you take this, put it over there, you can see that you actually are resolving the star disk itself. 2.3 milliarc seconds in size. As the eclipse started, you can start seeing this little sliver that's cut out of the star. And as the eclipse continues on, you can see that that covers the entire sort of southern hemisphere of the Eps Aur. It doesn't cover the entire Eps Aur. And we knew that wasn't the case, that we knew the Eps Aur wasn't being covered because the F spectrum continues even during mid-eclipse. So you know the Eps Aur is still present, but some of this light has been removed. And this is direct evidence that that's what's happening. The bright spots up here and the star here, I mean, you're dealing with a theoretical model of how you interpret the data coming off of these arrays. You don't have perfect resolution. You can't be sure that that's real. You can be sure of some feature that's this size, and that's what you get. Now, if you take all the observations that Brian has accumulated over the last couple of years, and you sort of stack them together so that you can you sort of fix it on the disk and then use the star as a probe of what the disk looks like. And you get an image like this. And so here are all the observations that he's taken. So, you know, the relationship between the star and the disk, and the relationship between the star and the disk a couple of years later, and you combine them together like this, you can actually get an image of what the disk looks like. And the disk does look like this big, thin cigar. And so, as far as we can tell, all the models of that shape really do fit. And this is an observational confirmation of that. But that's about all that we know so far. It's amazing. Here we've put in thousands of amateurs and hundreds of hours of professional telescope time, and we still don't have all the answers for the system. We're hoping that after the eclipse is over with, there will probably be a full-scale professional seminar conference dealing with the star, in which people will then present their information in addition to the amateur contributions, and will actually, maybe for once and for all, be able to decide whether it's the low mass scenario or the high mass scenario, and maybe get an idea of how the system formed. The problem with something like the low mass scenario where you're dealing with a evolved star is that these disks around stars don't last for very long. You get a disk around a star, it tends to dissipate after a while. So why is the disk there in the old star configuration? The young star configuration, that matches, but then some of the other features don't match. So I don't know what the answer is yet, and I think it's going to take some tweaking of models. In the meantime, we do need more data. So if you can think about observing the star, go over to the Citizens Guide website and sign up and start taking some data and contributing to the project. Epsilon Aurigae is just coming around the sun. It's usually July is the month that everything goes away. And now you can start seeing it in the early morning hours from our location. Like I said, any of the types of observations that you can make will be valuable and useful. And if you want any more information, here are a couple of websites. The Citizen Sky one, the ABSO one. I said that Jeff Hopkins is running a campaign. He does put out a newsletter of some of the more recent observations. And so here's his website and his campaign. I think if you Google on Jeff Hopkins and Epsilon Aurigae, this will pop up. And then, like I said, we're going to have a special issue of our journal, probably August of next year, in which we will have at least the amateur contributions to this project. And hopefully we'll get some professional papers in there as well. So that's all I have to say. I'm sorry I can't give you a good answer at this point, but it really is a fun system. Thank you very much.
time for a few questions.
Yeah. Has there been any spectroscopic deductions regarding things like the chemical composition of the cloud? The trouble with the cloud is that it's dark, and so it's not emitting any light of its own. So the only light that we have is either from reflection from the V star in the center, or we actually do see some indication of heating on the trailing edge of it as the cloud passes beyond the star. It is rotating on itself, and you can actually see it get heated from the Eps Aur and then rotate into our line of sight. And so we get a little bit of information, but it's just not enough to know more than green size, and that's about it. Any others? Yeah.
I may be displaying my ignorance, but has anybody thought about the possibility that the black cloud is actually forming another star?
So, has anyone thought about the possibility of the black cloud forming another star? Like I said, if you go with a high mass scenario, then you're dealing with a young stellar object. And so whatever is being formed in the center probably is still being formed and hasn't gotten down to the main sequence yet. So in that sense, yeah, there's a possibility that something is getting formed in the cloud. One of the problems there is that if you assume the grain size as being very large, that's kind of counter to what most people think is a protoplanetary dust cloud that tend to have small grains. And so, there's pluses and minuses. I think it'd be a neat scenario. But the problem with that is that if it's a high mass F star, then there has to be a high mass object inside of the dust cloud. And if it's a high mass object in the dust cloud, how come we don't see it? And so, it's a mystery. And so it's a fun one. That's why so many scientists have been looking at it and trying to figure it out. Here's a third magnitude star, and we don't know what it is. And so, if you look at that, then, you just wonder about some of the other things that we have put so much time and effort into. Here's something that anyone can look at, and they ought to. Are there any other systems that are remotely similar to this? I think I've heard of one, but I don't remember the description offhand. Let's put it this way, it's an extremely rare object if there are any that are similar to it. And I don't think I know of any, certainly none that have this kind of period and everything. I know of other systems where there is an accretion disk around them, but it's nothing like this. Okay, well, thank you very much.